So far we've looked at only expressing integer values, that is, whole numbers. We haven't looked at how to express fractional quantities, things like 3 over 5 or 22.81. And it's not obvious how we would express these because using just bits, we don't have any mechanism to specify how the numerator is separated from the denominator, for instance, or how the left side of the radix point is separated from the right side of the radix point. So we need to come up with some sort of scheme so we can tell these things apart. And as it turns out, there are 3 major schemes for doing this. The most straightforward scheme, I think, for expressing fractional quantities in bits is called rational notation, which is essentially we designate some number of bits to represent the numerator as an integer, and then we designate some other number of bits to represent the denominator as an integer. So say if you wanted to express the fraction 5 over 13, well, we would say, perhaps we'd say we use 8 bits to represent the numerator, so 5 expressed in binary is this, and then say 8 bits to represent the denominator, and 13 expressed in binary is this bit pattern, and so we have our fraction. Now, it doesn't matter that the denominator come immediately after the numerator. You could put the denominator before the numerator, or you could put the numerator and denominator in entirely different places in memory. It doesn't really matter as long as you remember where you put them. Nor should I say it doesn't matter that they both use an equal number of bits. You could have the numerator have 20 bits and the denominator have 3 bits. It's really up to whatever suits your purposes. The other 2 schemes for representing fractional quantities are called fixed point notation and floating point notation, and they both have in common that they use an implied radix point. I'm sure in your math class you probably learned to call this the decimal point, but it's more generically called the radix point because you would only call it the decimal point if you're dealing in decimal, but of course in the computer we're dealing in binary. But rather than call it the binary point, we call it the radix point to refer to this dot. Of the 2, fixed point is more straightforward than floating point, so we'll look at that first. In fixed point, you simply designate one set of bits to represent the left side of the radix point, and another set of bits to represent the right side. So far it sounds a lot like rational notation. However, it's not that simple. What's tempting to do using fixed, the way you want to think it works, is that we take 22, we translate it into binary, we write that as bits. Let's say we're using 8 bits, so this is 22 in binary, and then you want to say, well, let's write 81 using some number of bits. And here's 81 written in binary. Well, this would be straightforward and easy. It is entirely wrong, or at least this part of it is entirely wrong. Well, the left side of the radix point, yes, the translation is straightforward. You simply take the decimal value and you translate it to binary. However, when you convert the right side of a radix point from one number system to another, the conversion does not work the same as it does on the left side. And to understand why not, we'll have to look at number systems again. When I introduced positional notation to you, I explained it as a system wherein you had some limited set of symbols, and we wanted to count to infinity, and what we did is then we cycled through our limited set of symbols, and when one digit cycled from the highest to the lowest, we then cycled to the left, and so on, and you should remember that. Now, while I do think that is a good explanation, and in fact probably how the system was originally devised, it's really not adequate because it doesn't explain how what we would do to the right of a radix point. And for that we need a more systematic mathematical definition of positional notation. Here's how positional notation is usually explained. Say we have some number, 8302, and assume it's decimal. Well, this is equivalent to 8,000 plus 300 plus 0 plus 2. That gets us 8,302. This in turn is equivalent to 8 times 1,000 plus 3 times 100 plus 0 times 10 plus 2 times 1. And this in turn we can redefine as 8 times 10 to the third, 3 times 10 to the second, 0 times 10 to the first plus 2 times 10 to the 0th. And remember, 10 to the 0th, anything to the 0th power is equal to 1. So this is usually how we define decimal. It's each digit is multiplied times a power of 10, which is appropriate for the position of that digit. So because this is fourth from the right, it's multiplied times 10 to the third, and for each digit we add, it's a higher power of 10 is what we multiply that digit by. And once you multiply each digit times the appropriate value, you sum them all together. This is the way it works in all positional notation, no matter what the base. It's just that depending upon the base is what you use as the base of this exponent. So while we use powers of 10 in decimal, it would be powers of 2 in binary, or powers of 16 in hex, and powers of 8 in octal, and so on. Armed with this more mathematical explanation of positional notation, we can now say what happens to the right side of the radix point. So say 32.45. Well, this is equivalent to 30 plus 2 plus 4/10 plus 5/100, which is equivalent to 3 times 10 plus 2 times 1 plus 4 times 1/10 plus 5 times 1/100th. And this is in turn equivalent to, here we just changed 10 to 10 to the first, we changed 1 to 10 to the 0th, we changed 1 to the 10th to, is equivalent to 10 to the negative 1, and 1 over 100 is equivalent to 10 to the negative 2. So we have a consistent pattern here. As you add digits to the left of the radix point, the powers of the base increase, starting from a power of 0. So we go from 0 to 1, and then onwards to 2 and beyond. But then when we go to the right of the radix point, we go increasingly negative, starting with negative 1. So we go to start with negative 1, go to negative 2, and then we would go on to negative 10 to the negative third. So we have a consistent definition in positional notation. Each digit place is multiplied by the appropriate power of its base, of the base being used, and what that power should be is determined by the number of positions you are from the radix point. And then once you have those, once you multiply each digit times the appropriate value, then you sum everything together. There's a really important difference about conversions between number systems on the left side of the radix point compared to conversions between number systems on the right side of the radix point. Say we're just dealing with the left side of the radix point, that is, we're dealing with just integers, and say we're using some limited number of digits in whatever the number system, whatever the base chosen to express values. So say that in binary we're going to limit ourselves to 3 digits. Well, with 3 binary digits you can express the values 0 to 7. That is the binary equivalent of decimal 7. In contrast, 3 decimal digits, that gets you the values 0 to 999. So there's 2 interesting things here. First, in one system, the system with the higher base, you're going to get a higher range of values. The second interesting thing is that in this, the numbers and the values in this set are all present in this set. So say the value 5 is also found in this set of numbers. The number is expressible with 3 decimal digits. So while one set will have more values, the values of the other set are all found in it. Now let's say we're using a limited number of digits, but only to the right of the radix. That is, we're dealing with values that are 0 point something. Let's say we restrict ourselves to using just 2 digits right of the radix point. Well, in the case of binary, that will get you, you'll be able to represent the value 0 to as much as 0.75 in decimal. Let's see why this is the case first before we go on. If we have 2 digits right of the radix point in binary, then their maximum values are both 1 and 1. And this value is going to be 0 plus 1 times 2 to the negative 1 plus 1 times 2 to the negative 2. That is, this is how we convert to decimal. We use the same reasoning we did in decimal, we just changed the base to 2 instead of 10. So 2 to the negative 1, that is 1 over 2, and which is 0.5 in decimal, and 2 to the negative 2, that's over 1, that's 1 over 2 times 2, so it's 1 over 4, which in decimal is 0.25. So we're going to add 0.5 to 0.25 in decimal, giving us 0.75. So in fact, when we're dealing with two binary digits right of the radix point, that gets us 4 different possible values. There's going to be, because it's just going to be some combination of 0 and 0.5 and 0.25. So that gives us 0, 0.25, 0.5, and 0.75. Those are all the possible values. But now consider when we have 2 decimal digits right of the radix point. That gets us the values 0 to 0.99, and all the values in between there are like 0.11, 0.13, and so on. So what is the same here? Well, here the numbering system with the higher base got us a larger value using the same number of digits, just like it did on the left side of the left side of the radix point. And also the values representable in the smaller base system, they are all found in the same set of values of the larger base system. So you can have 0, 0.25, and 0.5 and 0.75 using just 2 decimal digits right of the radix point. But now here's the significant difference. On the left side of the radix point, while binary can't represent everything that decimal can using the same number of digits, there weren't any gaps. But now look here, what we represent in binary, we're leaving large gaps. So the lowest value representable is 0 and the highest 0.75, but there are values found in here, in this set, less than 75, which are not found in this set. Things like 0.33 and 0.2 and so on. So the moral here is that when converting values with fractional components from one numbering system to another, you not only have to worry about range like you have to do with integers, you also have to worry about accuracy. If you are limited to, say, 2 binary digits right of the radix point, and that'd be a pretty small amount of digits, but just for the sake of argument, you would have to be aware that not only can you not represent the same range of values as you can with 2 decimal digits, you're representing a smaller range of values, you can't represent all values in that range. And so you're going to have to either settle for an approximation, or you're going to have to rethink what you're doing, find some way to get more bits to use. Before moving on to floating point, I'd like to discuss how to mentally convert between binary and decimal and vice versa. Now that I've fully explained positional notation, it makes sense to do so. So first let's look at binary to decimal. So say you have this binary number, you look at it and you think, well, I have no idea what that is in decimal. Well, how could you find out? Well, the neat thing about binary to decimal conversion is that in binary you can really simplify things, because each position either has some value because the digit is 0, or because the digit is 1, or it doesn't have any value because the digit is 0. So really you can essentially ignore the zeros except for the space they take up, and you can really you just have to add together the positions with 1s in them, and it's nice because multiplying anything times 1 is really easy. So all you really have to know is what value each position has. So say left of the radix point, this position is worth 1, this is worth 2, 4, 8, 16, and 32, and so what we have left of the radix point is 2 plus 32. Similarly, right of the radix point, what we have is this position is worth 1 over 2, this position is worth 1 over 4, and then this last position is worth 1 over 8. So we have 1 over 4 plus 1 over 8. So we sum all this together and we get 34 and 3/8. Expressed in radix notation, that's 34.375. Now let's look at going the other way from decimal to binary, and say we want to convert the value 105 decimal to binary. Well, what you do is you mentally picture a field of digits which are unknown. So these are all unknown binary digits. Here's the radix point, and the first thing we can do is we can say, well, look, it's an integer, therefore everything to the right of the radix point, that's going to be 0. Now all these digits are going to be either 1 or 0, and what we need to do is find the highest value digit which needs to be set. So that means finding the highest power of 2 which exists within 105. That is, we need to discover what range 105, between what 2 powers of 2 105 exists. And the answer is that it's between the powers of 2, 64 and 128. Because it is less than 128, then you know that the 128 bit the digit place whose value is 128, that's a 0, and everything to its left is a 0, because if those bits were set, then you would end up with a value that's too big. So the biggest digit we need to set is the 64-bit, or rather the digit with the value 64. So having set this bit, we know that everything to the left of it is a 0, so we can ignore them, get rid of them. And so having accounted for the 64, which exists within 105, we then need to subtract out 64. And that leaves us with 41. So now what we need to do is figure, well, what's the biggest power of 2 that fits in 41? And the answer is 32. 41 is between 32 and 64. So we set the bit whose value is 32, and then we subtract out 32 from 41, leaving 9. And then same thing, we find out, well, what's the biggest power of 2 that exists within 9? And the answer is 8. So we set the bit whose value is 8. Excuse me, that's 1. And having set this bit, we know that everything to the left of it, that which we haven't already set, that's going to be a 0. And we subtract 8 out of 9, leaving 1. And 1, in fact, itself is a power of 2, so we know exactly what digit to set, and that's the first digit here. That's the digit that has the value 1. And having set this digit, we can fill in the rest to the left of it. And of course, when you subtract 1 from 1, you're left with 0. So having reached 0, we've accounted for the whole quantity. So we don't need to do any more work. So this is the binary equivalent of 105. So as you can see, both of these methods for converting from binary to decimal and decimal to binary, they rely upon you memorizing the powers of 2. And once you get into dealing with a whole lot of digits, like past, you're going to have to deal with very large powers of 2, and therefore the mental work becomes more difficult. So not only would you have to memorize more powers of 2, the arithmetic gets more difficult. Therefore, in practical terms, I would say you would really only do mental conversions when you're dealing with about maybe up to 2 to the 20th. So 20 binary digits left of the radix point. And that's about where it starts getting quite tricky for most people. In practice, I would say such a skill is really not that necessary, because if you use mental conversions at all, you're generally going to be doing it with small numbers. Still, if you understand conversions, then it really drives home the concept of the number systems themselves. So that's why it's a good thing to learn and practice.